mechanics. Today we will be discussing the work energy theorem. It says here the work done by the force acting on a particle during its displacement is equal to the change in kinetic energy in that displacement. Work done equals change in kinetic energy. In other words, the net work done on an object is equal to the change in the kinetic energy of the object. So here we have W net is equal to delta KE, where delta means change, KE is kinetic energy. But kinetic energy depends on speed, that is velocity, where velocity is speed in a given direction, and mass. So the formula is Ke is equal to half mv squared. Kinetic energy is equal to half times the mass, where m is mass, times velocity squared, where v is velocity. Kinetic energy is a scalar quantity. The SI unit of kinetic energy is joule. Let's look at example 1. A 7 kilogram bowling ball moves at 3 meters per second. A 2.24 gram table tennis ball also moves with the same kinetic energy as the bowling ball. How much kinetic energy does the bowling ball have? B. How fast must the table tennis ball be moving to have the same kinetic energy as the bowling ball? C. Is that speed reasonable for the tennis ball? Let's look at the solution. Let B be the bowling ball and T the table tennis ball. Then we can write M sub B is equal to 7 kilograms, M sub T is equal to 2.24 grams, and V sub B is equal to 3.00 meters per second. M sub B here was the mass of the bowling ball, M sub T, the mass of the tennis ball, and V sub B, the velocity of the bowling ball. For part A, the kinetic energy of the bowling ball is equal to half times the mass of the bowling ball times the velocity of the bowling ball squared. So that's going to be equal to half times 7 times 3 squared, and that's going to be equal to 31.5 joules. For part B, we have to first convert the 2.24 grams, and when you do that, divided by 1,000 gives you 0.00224 kilograms. Given that the kinetic energy of the bowling ball is equal to the kinetic energy of the tennis ball, then we can substitute 31.5 equals to half times 0.00224 times V sub t squared. V sub t squared here is the velocity of the table tennis ball, which we want to find. Continuing with our calculation, we have 31.25 rather on the left side equals 0.0112 VT squared, where the half of 0.0224 gave us 0.00112. To find VT squared, we divide the 31.5 by the 0.00112, and that gives you 28,125. Find the V of t, we take the square root of 28,125, and that gives us 167.7, and that is in meters per second, the velocity of the table tennis ball. For part C, this 167.7 is extremely fast for a table tennis ball. Because, table tennis ball is really light and does not move at that speed. That speed is too fast. Let's look at some more ideas under the work energy theorem. So when work is done by a net force on an object, the only change in the object is its speed. The work done is equal to the change in the object's kinetic energy. The speed will increase if the work is positive, and it will decrease if the work is negative. The formula here is W net is equal to KEF minus KE sub I, and that is your change in kinetic energy, where KE sub F is the final kinetic energy, and KE sub I is the initial kinetic energy. We know that W net here is equal to half mv squared minus half mu squared, where v is the final velocity and u is the initial velocity. An example, the driver of a 10 to the third kilogram car traveling on an interstate, that's a highway, at 35 meters per second, slams on his brakes to avoid hitting a second vehicle in the front of him, which has come to rest because of a congestion ahead. After the brakes are applied, a constant friction of 8.0 times 10 to the 3 newtons acts on the car. Ignore air resistance. In part A, at what minimum distance should the brakes be applied to avoid collision with the other vehicle? And part B, if the distance between the vehicles is initially 30 meters, at what speed would the collision occur? So now let's do our calculations. Our given information is U equals 35 meters per second. V will be equal to 0 meters per second. M is equal to 10 raised to the 3 kilograms. And a frictional force is given as 8 times 10 to the third newtons. So note that frictional force moves in the opposite direction to the motion of the vehicle, so it will move in a negative direction. Here, using our formula, W net is equal to half mv squared minus half mu squared, and plugging in the information, substituting negative values for friction, negative 8.0 times 10 to the 3. We could say now, apply a negative here. Even though it's given as a positive, we know it's moving in a negative direction, so we can apply it there so that the answer that we get will be sensible. So we have negative 8 times 10 to the third times d is equal to half times 10 to the third times 0 squared rather, minus a half times 10 to the third times 35 squared. And so negative 8,000d is equal to 0 minus 612,500. So d will be equal to negative 612,500 over negative 8,000. And so our distance would be 76.6 meters. Part B, our network here, using this formula, network is equal to half mv squared minus half mu squared. So negative 8 times 10 to the third times 30, substituting the information, is equal to half times 10 to the third times v squared minus a half times 10 to the third times 35 squared. Our aim here is to find v. So calculating left side, negative 24,000 is equal to 500 v squared minus 612,500. So 500 v squared is equal to negative 24,000 plus 612,500. And so 500 v squared equals to 372,500. So to find v squared, you divide 372,500 by 500. So v squared is equal to 745. Now to find v, we take the square root of 745, and so that is equal to 27.29 units meters per second. So here now, velocity would be 27.29 meters per second. Thank you.